All right. My name is Andreas Köpfer, and I'm happy to welcome you to today's workshop by Oliver Rittmann entitled Computationally Analyzing Politicians' Body Language Using Pose Estimation. The Social Science Data Lab is an event series at the Mannheim Center for European Social Research that provides a platform to researchers to present tools and methods for the collection, management, analysis, and visualization of data in social sciences. Our presenter, Oliver Rittmann, is a Nobel Prize Fellow at the MSES. In his research, he uses computational methods to analyze large-scale audio and video corpora of political speeches, exploring the nonverbal communication strategies of politicians. In his talk today, Oliver will give a brief technical introduction on how to analyze politicians' body language in video recordings using pose estimation. He then walks you through an interactive coding session where you estimate the pose of different MPs, and you also learn how the resulting data can be used and analyzed to meaningfully quantify political speech. Short disclaimer, we are recording this live stream in an active speaker mode. Audio from on-site and remote attendees will be recorded, and if your video is on while asking a question online, your video will be recorded as well. For those joining us online, you may ask your questions by raising your hand or posting a question in a Zoom chat, which I will then read out for you. And finally, with that, floor is yours. Thank you.
Thank you. Thank you all for coming here online. So this workshop is going to have two parts. I'm going to give a short input presentation to motivate what we're doing today. We're going to use computational tools to analyze politicians' body language during political speeches. But the input talk explains what we're doing and it motivates what we're doing. Why are you interested in analyzing the body language of politicians? This is the first part, around 10 minutes only, and then we'll have a coding session together. It's very nice to be here. It's the first time so I've been developing this for quite a while now. It's the first time that I'm teaching this to others, so preparing the code for others. So I'm really looking forward to seeing how it goes and how you feel about the code. The code will be primarily in R because I feel much more comfortable working in R, but there's no way around some Python. So we'll start with some Python coding. This will all be in Colab, so you don't need any Python installed on your computer. And then we work in R. All the materials will be available on the GitHub repo, and you can code along if you want to, but you can also just follow me if you don't want to. Okay, so let's start. Why would you be interested in computationally analyzing politicians' body language? If we ask ourselves, what makes a good political speech? When is a political speech good? Prepared political speech, for example. The first thing we need to come up with is the content of a speech. At the text of a speech, we need to decide what we want to say in a way that hopefully resonates with the audience and communicates our results. Not our results, but what we like, the positions we want to take, and so on. If we want to analyze this part of a speech as political scientists, we need to analyze the text of this data, and this has been happening in the past decades in political science and the social sciences quite extensively. Many of you are doing this in your own research. However, even the most well-written speech won't have a great impact, won't resonate with the audience if the delivery isn't good. And the delivery is more than just the words of a speech, but it's also how you kind of pronounce these words, how you modulate your voice, whether you speak emotionally and whether you use gestures or not. But this adds more layers of data, like how you modulate your voice. That's not necessarily in the text of the speech, but it's in the audio recording of the speech. And whether you use gestures or not, this is kind of in the video recording of a speech. It's also not necessarily captured in the text of a speech. One theme of my research is that I want to not restrict the study of political speech to just transcripts of speeches that give us an idea about the content of speeches, and that's clearly valuable, but to also make accessible this audio dimension and the video dimension. And today we are going to focus on the video dimension and want to build a tool that allows us to quantify what sort of body language speakers display when they give political speeches. This is based on a broader project. There's a working paper that I will link later where I kind of develop a framework, my idea about how this can go. There are many ways one could kind of try to analyze body language or other nonverbal cues in the videos of speeches. In this paper, I developed one idea. And this results kind of in a framework, course of action that we can follow if we want to do this. Since there are many ways one could kind of start doing this, to find my way, the way I want to do this, when I started this, formulated 4 goals, 4 desirable properties that I want to achieve when I do this. The first one is I want a method that's scalable. I want to analyze body language in videos on a large scale, similar to what text as data approaches have been done. And this basically means some computational approach where we don't have to look at or watch every single speech that we're interested in and hand code them, but a computational measurement pipeline. I want this to be versatile, first in the sense that different aspects of body language that we need to define, different measurement targets can be measured, and versatile in the sense that we can apply it to different cases. Today we'll analyze speeches in the German Bundestag, but it would be great if we could apply those measures that are developed in the Bundestag or applied to the Bundestag, could also be applied to speeches in other parliaments to facilitate comparative research. Thirdly, the measure, of course, should be valid. So whatever variation we generate, this should be in line with what humans or audiences perceive when they observe speakers. And fourthly, and this is important for me, I want a measurement approach that gives us transparent and interpretable variation. We want to understand where the variation comes from. We want to understand theoretically what high values and what low values mean. And this means I don't want a pure black box model, like a pure supervised learning black box models, but something that's more open and that we can actually interpret. Okay. The framework that I developed in this broader research project focuses on body language. It allows to analyze other sorts of nonverbal cues, for example, the voice as well. This framework focuses on body language, and this workshop will also focus on body language. Okay. So the key challenge that we face is that we have video data. We can all, as humans, we know how to process video data and form our perception of a speaker. You already did this in the previous slide. The key challenge that we have if we want to kind of extract information from this is that this, in terms of data, is very unstructured. It's just pixels, but we want to extract information on the body language from those pixels. The key idea of my approach, what we're doing today, is to apply something that's called pose estimation. Pose estimation are models developed in computer vision, and they are readily available, pre-trained. We can download them and apply them. And what they do is they detect and trace key points of the human body in images or throughout videos. That's shoulders, elbows, wrists, eyes, and so on. You see very clearly and intuitively what happens. I think that this is very useful because it reduces all the information that's in the video to precisely the information that we need if we are only interested in body language, because all the gestures, if you look at this frame here, they are in the pose estimation, this key point representation of the speaker, just as they're here, but all other data is kind of deleted. And when we apply this, we can use the remaining data, which is much less, to quantify body language. Okay, so the framework I developed basically has 3 steps. In the first step, we need to define what do we actually want to measure. Up until now, I just said body language, but this could be anything. Since this is an interpretable or transparent method, it puts us into a position where we very precisely need to operationalize what we actually want to measure. Here today, also in the paper, we're measuring something that I label the speaker's nonverbal effort. And when we watch at those two short video sequences, also the video sequences that we later will use in the coding session, on the left side, we have a speech where we could say this is low nonverbal effort. There are not much gestures going on. It's a rather calm speech, whereas the speaker on the right side puts much effort into the speech. And to give a kind of definition, we want to measure whether and to what extent the speaker uses nonverbal cues to make their speech nonverbally appealing without specifying the nonverbal cues in itself. It's just activity in the first place. Okay. In the second step, we need to operationalize our target. So what contributes to high nonverbal effort? And here we can come up with different indicators. One indicator could be gesticulation. And I define this as the dynamic use of gestures specifically through hand movement. And I think that the data that we get from those pose estimation models is very useful here because this movement in different parts of the body, including movement of the wrist, is captured by those representations. It's captured if you look at this gesture here, it's captured by the fact that from frame to frame, those are 6 frames, there's location of the wrist changes, which tells us there's movement in the wrist. And the higher the distance between 2 consecutive frames, the more movement was there. So here, there's quite strong movement because there's distances between the points. The left wrist remains in one position, so the distances are basically 0. So we can calculate those distances between frames, calculate the average, for example, and this would give us an idea or an indicator telling us there's movement in the right wrist, no movement in the left wrist. So it makes use of this fact and then constructs an indicator of gesticulation, which is just the average between frame distance of the locations of the wrists. Okay. Second indicator could be posture. Gesticulation is just about movement, but not really about the form of the movement. You could move your arms down here or up here, but if you do it like this has very different effects on the audience, and posture is an indicator that's supposed to capture this, defined as the adoption of strong postures that increase the speaker's body size. Again, this can be quantified based on pose estimation. Here we see that with the right arm, there's this body size increasing posture, and it's body size increasing because it's an upward movement. We can quantify the height of the wrist relative to other body parts. So I do this here relative to the shoulder. So this here is above the shoulder, the left wrist is below the shoulder. We can again use this and quantify this by taking an average of the wrist height. I do this by taking the average of the higher wrist, so whichever arm you raise, this gives an indication of whether you increase your body size or not. Okay. In the third step, we're not going to do this today, but this is pretty simple. We can combine those different indicators that we develop to an index. Okay, so this is what we are going to do. Again, there's a paper that develops this further, explains everything in more detail, and also has an application, also a validation. I'm not going to talk about this in detail to have more time for the coding. But yeah, there's a validation, and then there's an application where I apply this framework to many speeches in the Bundestag, 30,000 speeches. I'm interested in studying the relationship between what speakers say on one hand side and how they say it non-verbally on the other hand side, particularly whether there's a trade-off between the complexity of the arguments that are put forward on the content side and the non-verbal appeal, the non-verbal effort that is put into those speeches. And what I find is that there's a trade-off between the two, in the sense that if speakers focus on putting forward complex arguments, and this comes at the cost of nonverbal appeal. But if they give nonverbally appealing speeches, then their arguments will be less complex, typically. Opposition speakers tend to focus more on nonverbal appeal, less so on complex content. And government speakers, they present more complex content, but with less nonverbal appeal. Okay. This is a point where I could welcome questions if you have any questions. Comments? Yes.
I have one comment. I'm wondering, this nonverbal appeal means nonverbal effort, right? That people put in speeches.
So it's two different things. So nonverbal appeal would be more on the perception side. I perceive something as nonverbally appealing. Nonverbal effort, as I define. So speakers put effort into their nonverbal delivery with the goal of making their speech nonverbally appealing. Whether they achieve to do so or not is a question that I don't answer in the research. And I kind of assume if they use gestures, then they do this with the intention of making their speech nonverbally appealing. Can be successful, cannot be successful. That would be another question.
Okay. Because I was just thinking about this. There's this one super famous speech by Netanyahu at the UN General Assembly, where he just stares them down and doesn't move and doesn't say anything for, I think, a couple of minutes. So that would be no effort as by this measurement, right?
Yeah.
Okay.
No non-verbal effort, yeah. Yeah, it wouldn't be captured in movement, yeah. Yes.
Yes. So one quick question on maybe the validation and the aggregation of the score. So currently the score being additive of the two features implies that they are not related. So the effort doesn't matter if I move my hands down here or up here.
Mm-hmm.
And given the rationale behind at least the posture part, whether you have also explored whether maybe the impact of the gesturing is stronger if the posture is more
So
I don't know.
in the paper it's validated against like human annotations. And so I do this additively in the paper because I want to push the idea to the limit to make this as simple as possible, but this doesn't mean that I say you have to do this additively. I also, in an earlier version, I had as many indicators as I could think of, and put them into a prediction model with interactions and everything. This would end up in a better score in terms of root mean square error or whatever, but it would come at the cost of interpretability. So it's a trade-off. I'm fine with both, but here I wanted to kind of stress the idea to do it as simple as possible. That's the only reason behind it. There are, of course, other ways to combine measures or indicators. Okay. In this case, we can move on to the coding part. If you want to code along, you're welcome to do so. All the material is in the GitHub repository. The link is here. Prerequisites, as I said, is an installation of R in our studio and a Google account for Google Colab. I'll give you, Andy posted you posted the link, but you're not on Zoom. I will wait for a couple of seconds so that you find the link. Okay, so this is a GitHub repository. It contains quite some files, but not too many files, actually.
Spider.
Hmm?
Spider.
Oh.
Babytarantel, würde ich sagen. Zum Glück ist die andere Tür. Yeah. 0 efforts.
High effort, lower fear.
Okay, so I'm in my folder structure. This is the directory. This question. I'll try to answer the question.
You want to answer it now? Or?
I think.
Yeah. You can also read it like.
Oh.
Yeah. So there's a question in the chat. So politicians and analysis claim that you can tell who wins a debate by watching with the sound off. These measured body changes capture excitability or passion. Do they also capture dominance or assertions of authority?
So I think they do, yes. But the idea is always to take the data and then think about what you want to measure. If you want to measure authority, then you would have to define, okay, what sorts of gestures and what sort of movement patterns reflect this. I think of the two indicators that I presented, the posture one that says, okay, you need to take body size increasing postures. That's more an assertive style of communicating if you do this. So this would be something that you could use to do so. But the key is that you need to be able to very precisely define what sorts of gestures you want to quantify. And if you're able to do this, then I think there's a way to define patterns in the movement that you want to extract from this data. Okay. All right, so here's the repository. There are different things. You find the slides here. There's a video folder, and there's a result folder, there's a model folder. Those are the important things for now. In the video folder, I'm going to open it. And there are a couple of things. The most important thing are those two videos. They're the speeches that you've just seen. And they're the speeches that we'll use to apply the entire pipeline today. I'm going to play them quickly for you so that we all know what we're talking about. The sound's not working, but we're not analyzing the sound today anyway. So this is 10 seconds. So yeah, 10 seconds of speech where not a lot is going on in terms of nonverbal behavior. There's a little bit of movement, but it shouldn't lead to high scores in any of the indicators that I introduced. So this is speech 1, Gabriele Heinrich. It's a speech in the German Bundestag. Second speech, about the same length, also 10 seconds, Klaus Ernst, and again, Bundestag. Many things going on. If like those indicators are in any way meaningful, then they should very clearly give different scores to those two speeches. So we're going to take those and apply post-estimation to them, like retrieve the data and then explore the data a little bit and see how we can work with it. The goal really is to, on one hand side, give you a pipeline that you can use for your own speeches if you want to use post-estimation, and then get a feeling for how the data looks like, how we can work with it, how we can visualize it, and so on. Okay. So we are going to start with, so we are now in the timeline. We are finished with the input talk, and we're in the hands-on coding session, which has two parts. The first part will be done in Python, which is the application of post-estimation. To do this, I want you to follow the link that is linked here. And this will, I actually do it in a different tab. This will bring you to, I think I do it like this, to Google OLAP. It only runs if you are logged into a Google account, as far as I know. It's connected to my GitHub, to the respective repository, and we can now open the Python notebook that's called SSDL post estimation. It's also in the repository. If you want to run it locally, this also works, but it will be more complicated. Okay, so this is one Python script not too long. The only purpose of this is to read in the videos, apply post estimation, store the data, then we can download the data. It's actually already in the repository, and then we'll go back to R. This is kind of how I work. It's not necessarily the most productive way. Everything we do later in R is probably also possible in Python, but it's not my preferred way of doing it because I'm just more comfortable in R. Right now we have no data other than the standard Colab data loaded into this Python notebook, but we can, the first thing we are doing here is we clone the GitHub repository and thereby downloading or loading everything from the repository up to the Google Colab notebook. This also includes the 2 videos that we can then work with.
While we're waiting, there is a follow-up question on the question before. Basically, does it also capture facial movements, or could it?
So facial movements are not captured by this model. The overall framework, where you say, okay, you define measurement targets, then you think about how can we quantify them. In this framework, using post estimation is one way where we can transparently quantify aspects of body language, but not facial elements. For that, you would need other models that do this. They are available, but they are not I haven't done so in my research. Okay, so this is done. We now have, so if you click on this folder here, we now have the SSDL body language folder with all the files from the repository, including the 2 speeches that we want to work with. So speech 1, speech 2, MP4 files. Okay. We need to, one other thing that's worth mentioning, in the model folder, there is a file that's called light model movnet single post thunder3.tf-light. This is the pre-trained model. You can download it. It's also linked in the text. It's from TensorFlow. It's a MoveNet model that we're using. It's nothing that I trained. It's readily available. We just need to download it and load it into our environment. We're going to start by importing some dependencies. Nothing really exceptional. TensorFlow, because it's a TensorFlow model. NumPy, matplotlib is something that I think is actually not even used. CV2, that's a computer vision library. That's critical because we're using video data, and this allows us to load video data into Python. Then there's JSON, because this is the format we want to store the resulting data later, and some OS and FNMatch. They're not really special. Okay. So far, everyone who's coding along is good? Nice. Okay. So first thing we do, we load and prepare the post-estimation model. Again, it's stored in our repository in the model folder. And we, it's the object interpreter that stores this model, so we can use it later. And then there's really only one larger function. It's not so large. It's large because I added many comments that explain what's going on. It's called a function that's make key point detection. As input, it takes the path to a video that we want to analyze. If you want to analyze any of your videos, all you have to do is to put them into the videos folder, and it should work. It creates an empty list object, output images. This is going to be a list of images where one image is basically the key points of one frame. And this is the object where we store our results later. In the second line of code, we will create an object that's called cap. It's a video capturing object. This loads the video into Python. Loading the video into Python means that we do this frame by frame and analyze each single frame. So it's not all at once into the environment, first frame, second frame, third frame, and we just can apply post estimation to each single frame. While doing so, we initialize a loop. It's a while loop. It loops through the frames and it's open until there's no frame left of the video. So we go through each frame of the video. We use cat.read that just reads the frame. It gives us an indicator whether we read the frame correctly, and the frame itself. Frame is what we want to work with. Here's a little bit of code that just checks whether we read the frame without any problems. If there was a problem, it will stop the loop and we don't go on. If this thing here is true, indicating that we read the frame correctly, we move on. We create a copy of the frame just to not destroy or change anything of the original video. Call it image. So img image is now the frame we want to analyze. Before we can feed it into our model, we need to resize it. And this is because the MoveNet model that we are applying requires a specific image size. That's 256 times 256 pixels. And this line of code brings it to that size. It also includes some padding, so adding empty areas on top and at the bottom, because the initial video is not a square video. Okay, so img is now in the size that we need, which means that we can put it into the model. To do so, one thing we have to do is to put it or transform it to a float 32 tensor. Tensors are kind of the data format that go into those models. We set up the model itself, get input and output details. Nothing exciting. And then this bit of code here is where we apply the model. We set up the tensor, we invoke the model, and then here interpreter get tensor. So this here basically will be the result object, key points with scores. So once this is run, here we have the kind of the key points that we want. That's all. We need to store this or put it into the list. Again, we have a list output image that has one entry for each frame. One frame will be a matrix, or actually, I don't know, later it will be a matrix that scores those key points together with confidence scores. And so for each frame, we just append the output. So later this will be a list as long as the video is in terms of how many frames are there. Okay, cat release will end the video stream once it's we run through all the frames and return the output. All right, so we run this. We have the function. Now
Much of this was already asked, but regarding the frames, normally they have can you specify the frame rate somewhere?
The frame rate is, so there's a frame rate in the video. And here we just analyze every frame. And this information, so applying this function, like the frame rate doesn't really play a role for this. It would play a role for the application if we have 1,000 videos, 500 have one frame rate and the other 500 have another frame rate. The distances of key points between frames, for example, they're sensitive to how much time passed between two frames. So we should make sure that they are in the same frame rate. But for applying this, it doesn't really play a role.
Frame rate is
so these videos have a frame rate of 25 images per second.
And you also did the large analysis with the same frame rate. So we have 25 times 30.
Yeah, they are always 25 frames, yeah.
Okay.
Yeah.
Do you think there's an impact if we reduce the frame rate?
So from the application that I did in the paper, I actually discarded every second frame. So I have half the data that I need to process, but I'm actually not so sure how much difference it made in terms of processing time, because I never really tried to make it as quick as possible, but this was one idea to make it quicker. Yeah.
So is it a, yeah, sorry, there's another question, or is it like,
Should be fine, yeah.
because then I think it also, if you reduce the frame rate, you probably sometimes also capture, like some movements are happening at a faster pace, right?
Yeah.
So probably there's sensitivity regarding that, and
Yeah.
maybe sometimes it's also could have the same effect as make it more robust, or yeah, also like a deep learning.
Yeah, I think if you reduce the frame rate, there should be some validation always, and then you should validate it with both frame rates. So with the maximum and the mid, like the one that you opt for. It shouldn't be like at some point it won't work anymore, because you lose information.
But if you like deliberately like decrease the frame rate, it could also serve like kind of as a, can also do it because you want to do so, because you say maybe it's more valid if you have like less frames and you capture like more or less granular, more general behavior that you're more interested in. Is it like also rational like that, or
Maybe, I don't know. I mean, in the end, you discard information. I don't think there can be a big gain from discarding information, usually. Maybe it makes things more straightforward, but I don't know. All right. So we have our function. What we do next is we get our video files. We have 2 video files. I just retrieve them from this videos folder. If you would put more videos into this, we would have more videos here. So this video files is a vector just containing the names of the 2 files that we want to analyze. And then I wrote a loop that loops through all those videos. In this case, it's only 2, could be more. Not a lot of things happening here. We create the path to this file. So like the folder structure, SSDL body language is the first folder, video, second folder, then the file. Then it prints a message that just tells us, okay, we're now starting the inference for the first video, for the second video. We apply the function that we just coded, make key point detection, store the results in an object, and then here we store the result in our repository as a JSON file. We delete the temporary result file and print another message that just tells us, okay, we're done. The first video, the second video. If we run this, you will see that this takes a bit, but not super long. I actually don't know like what Google Colab works with. On my computer, it was so it like the 30,000 videos. They took quite a while to do, but they're like very, very long. But it's like less than the runtime of the video. I think it's like half the time. So if you have 1 minute video, it was like 30 seconds, something like this. Okay, so yeah, first video is already done. We're now in the inference for the second video. Also should be done. I don't know. It's like default Colab settings. Yeah, so 46 seconds, both for like 20 seconds of video in this case, so twice the time of the videos in this case, on whatever this runs on now. Can be faster. Sure. All right, so what we did now is we stored the results in a folder that's called MoveNet results. It's this file and this file. We can't actually be sure because the files were there in the first place, but you can trust me, we wrote those files again. So speech 1 and speech 2. This now contains the output data of this pulse estimation. And this is everything we wanted to do in Python. You can download this or put it back into GitHub, but it's already in the GitHub repository. So we're changing back to R now and explore what this data looks like. Okay, so I'm going to close this and I'm going to switch to R. To give you, so this, we are now in the repository still. This is the file called script RMD. It's in the first, like in the main folder of the repository. I'll give you a second if you want to follow along. Everyone's good? Okay. So again, we stored the data in JSON format. We're going to read those two JSON files, first speech, second speech, and store them in objects that are called speech 1 raw because it's the raw data, and speech 2. Those are weird objects. We can check the dimensions of the objects. It's 274. So this is the first speech, 274 times 1 times 1 times 17 times 3. First question, any idea what those dimensions of the object could be about? So this stores lots of data in these dimensions. Could it be? Yeah.
Frames, the first one, and then maybe the number of speakers, if there's like speaker identification or like body identification.
First one is correct. So first video is 274 frames. The second video has 267 frames. There's only one speaker, so we have, those are the videos here. There's only one speaker. It's also, the model was called single pose. That means it can only detect one pose. So if there are more, then it will just go for one of them and detect it. So there's always only one pose. We have, so those are basically empty, they don't matter. 17 is the number of key points that we are detecting. And 3 is because every key point has an X coordinate, a Y coordinate, and a confidence score. The confidence score tells us how confident the model was in detecting the speech. So if we subset this first speech object to the very first layer, or like the first entry of the first dimension, this is what it looks like. It's a matrix, 17 rows, each for one key point. X coordinates, Y coordinates, and the confidence level. Those 17 key points, they have a, like, you know what they are. They start with the nose, 2, 3 are the eyes, 4, 5 are the ears, 6, 7 are the shoulders, 8, 9 the elbows, 10, 11 wrists, and 12, 13 hips. This is all the upper body. And then we also have lower body parts, 14, 15 are the knees, and 16, 17 are the ankles. Those videos, as you can see, they only show the upper body. So everything up until here. And we can also see, if we look at the third column, the values here are fairly high. But so the knees and the hips, we have very low confidence scores. They're just not really detected. So this tells you, illustrates how those confidence scores are informative. They basically tell us the model has no idea where the hip, where the knee is. Those videos, but we also don't use this data today. Okay, this data format is not very convenient to work with. So the first part that I'm doing is quite some data wrangling. I'm not going to talk about this in detail, but what I'm basically doing is I'm looping through this list and I'm creating a time series out of the data so that we have time series of each key point through the videos. This is a function that's doing like this data organization for us. Then we apply it to both speeches. What does the result look like? It looks like this. We have some meta information, the file name of the speech that we are looking at, a running number for the frame, which frame we are at, what's the timestamp of this frame to calculate this. For example, so somewhere, where is it? So here, video length, it's actually 25 frames per second times. This here's the number of frames. By specifying this, I can calculate timestamp of each individual frame. And then we have a variable key point kp1x, that's the x coordinate of the first key point, x coordinate of the second key point, and so on. And if we go on, we get the y coordinates of those key points. And we also have the confidence scores of all the key points. And each column is a time series, frame, 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 frame. All right, does this make sense? So we want to visualize the data to get a feeling for how this looks like. In the repository, I also included all individual frames of those videos. This is something that you usually don't need, but it's helpful to visualize. We can visualize any frame that we would like. We just use the first frame. If you work with this, you can change the number and use any number to look at different frames and see how the key point data looks like. So we want the first frame. Frame file name gives us, like, this is, if you look into the folder, this is how those files are named. Frame 0001 PNG, that's an image of the first frame. And we can load this image with load image into R. I don't know whether you like work with image data in R, but it's actually not so difficult to load images and plot images in R. The image, again, is not an object that we work with every day, but it's not so complicated. It also has dimensions. The first two dimensions are the size of the image, so how wide is it, how high is it? So this has 720 pixels on the x-axis and 400 pixels on the y-axis. That's the kind of original format of the video. And we can plot the image quite easily just with the plot command and the image object. Yeah.
And what happened to the 2x6 times 2x6?
This only, so we loaded the video into Python. Within Python, we downsized the image, applied pose estimation. But we didn't change the original video. So this is why this is still in the original format. But we will see that, like, the pose estimation data will be on different scales in a second.
Just a question regarding those body key points. Are those 17 kind of like set? Or
for this model, yes, there are other models as well. I think, for example, there's also models that have more key points in the face for facial recognition things, but it depends on the model.
It's like high, low, like for other, like
I think it's pretty standard. Yeah. Okay. There's one thing to notice when we plot this particular frame, which is on the axis. The y-axis is reversed. This is because by some convention, the root point for images is in the top left corner, and then it increases to downwards and increases rightwards. This is why we have like a reversed y-axis, and we need to keep that in mind for the data, for the key point data later. Okay. So this is the first frame of the second speech. We are now also extracting from this time series data set only the first frame. So frame number is 1. We want the row from this data set that has frame number of 1. So key points is just a 1-row data set with the key points of this very first frame. We do this because this is the data we now want to plot. This data is not in the perfect format for plotting now, because like every x and y coordinate is a separate variable, which is why I once again do some data wrangling. First, I subset to only the first 13 key points, which are the upper body key points. We're not interested in the knees. This is in this chunk, so key points 1 to 13. And then I create a new matrix where instead of having this wide format, we now have one column for the x coordinates of all the key points, one column for the y coordinates of all key points up until 13. And this is now easier to plot because we can call the x variable and the y variables to get the locations of all those key points. Okay. So let's plot it. This here will just plot the data as it is without a lot of context. We are now kind of building towards, like, we want to get an understanding of what this data looks like. And part of this is seeing that if we just plot it like this, it looks a little bit weird. We could try to make sense of it. Can put the other image here. It's not here, unfortunately. So this is the image. This is what it's lost. It's supposed to look like. Yeah, we don't really recognize it. Maybe we do. In the images I showed earlier, we had those lines connecting specific key points to make it more approachable. This is what we are doing next. Here is a list of all the connections that we want to draw. So 1, 2, 1 is nose, 2 is left eye. We want a connection between nose and left eye, nose and right eye. So those are all the lines we want to do. And we're adding them in a loop here. It's quite some code, but this is what it generates. Still not really a human, but maybe you can figure out what's happening. And yeah, it's upside down. The reason for this is that we didn't swap the y-axis yet, but we also need to do this with those key point data. To do this, that's actually not so hard. By specifying the y limits, instead of 0, 1, we do 1, 0, and then it automatically draws the y-axis from 1 to 0 instead of 0 to 1, or however you want to put it. And then we have this little icon already. Okay, so some representation. This makes sense. In the next plot, I put both images side by side so that we see that like this matches. This is the first frame. This is the key point representation. Regarding the earlier question, we also see this here ranges from 0 to 400 and 0 to 750, so kind of the pixel space. And here we have everything in a square scaled from 0 to 1. So pose estimation output, original input, not on the same scale. That's not a problem. But if we would now want to put this here on top of that image, then we would have to rescale it. We would either need to downscale the image or upscale the key point data. I am going to upscale those key points with 2 fairly simple functions. Requires a little bit of thinking on how to do this, but all we need is like how wide and how high are the images, and then we can do this. So here we are calculating the scale key points. And this will allow us to put the key points on top of the original image, and we see that this works quite well. How are things going for those who code along, or any questions? Yeah.
So you said you don't want the black box, but isn't like a what was it, TensorFlow model still a black box to us?
Yeah. So
maybe not to you, I don't know. But
no. Certainly, but we have so we know what we are working with. We don't know how. I'm totally willing to pay the price of not knowing how exactly this model learns that the hip is here and the wrist is there.
okay.
But later, when I have the measurement and I can trust those locations, that I know, okay, I'm quantifying movement in the arm, even though I don't know how this exactly, like this is a black box, but in the end, the indicator is still like interpretable.
And maybe just we're talking about it, but is there some kind of uncertainty? Well, I mean, there are like the uncertainty.
So we have this confidence score, and I like in the paper I use this. But those confidence scores, for example, they range between 0 and 1, but they cannot really be interpreted as a probability or as an error range, or like we cannot construct confidence intervals from it. And so it's really difficult to kind of quantify uncertainty in this. All
like sort of like a cutoff value or some kind of
yeah, so I implemented like a series of filters with the goal of getting rid of all detections where I think that they could be unreliable, and then I would discard them. That's not really a quantification of the uncertainty, but just discarding detections where I think this adds noise that I don't want to have. How well this works, I don't know, but it's necessary. For the implementation, the entire implementation pipeline, for example, also has a classification model that tells us, does the camera actually capture is it this camera perspective or is it another camera perspective? Because all other camera perspectives, we couldn't analyze them. What sometimes happens is that a person walks by, like half shown, and then the detection would jump back and forth, and this would create implausible distances between key points from frame to frame. So I defined a threshold. When is a distance between two wrists from frame to frame too far to be generated just from movement? It has to come from measurement error or because another person was in the image, and then I wouldn't use that distance. So those are a couple of things. They don't really quantify uncertainty. It's a mean to handle misbehavior of the model in a sense. Okay. We have 30 minutes, right? Perfect. Okay, so what we did now, we loaded the videos into Python, applied post estimation data, and we loaded it then back into R, and now have some feeling about how this data can be represented in different data frames. What we want to do next is we want to consider the time series of those key points and calculate the measures that I talked about at the very beginning. So the measure of gesticulation and the measure of posture. Okay, to quickly repeat, I construct the measure of gesticulation by considering the between frame distances of the wrist and calculating the average. So the distance is an indicator of the movement, higher distance, more movement. And for the sequence, I calculate the average distance from frame to frame as an indicator of how much gesticulation is there in the video. To do this, the first thing we need is a function that calculates distances between 2 points in the two-dimensional space. That's the Euclidean distance. And here's a function that's calculating the Euclidean distance here.
It's like maybe useful to also consider other distance.
I thought about it, maybe, but I don't know. I think this is straightforward. Okay. What we do next is a function that takes as input the key point data. That's the time series data that we looked at earlier. We can have a second look at it, just to remind ourselves what it looks like. So we have variables, key point x coordinate of 1, second x coordinate, later the y coordinates. And from as we go down, we have the different frames and those locations. So what we are doing is, so the Euclidean distance takes the x and y coordinate of one point and the x and y coordinate of the other point that we want to calculate the distance for. x1 and y1 are the coordinates of the first point. And this is just key point 10 x coordinate of key point 10, that is the left wrist, and y coordinate of the left wrist. So this is the first. And then the second point are lead of the same key points. Lead will be just the next one. So first frame, second frame, third frame, fourth frame, and so on. If we run this, it adds another variable. Oh, yeah, this doesn't work. So it adds the variable left wrist movement. For each one, this is just how much is the left wrist going to travel to the next frame. And we're going to do the same thing for the right wrist, and just add the variable to the key point frame and return the key point frame. If we apply it to both speeches, we can look at the data again. I'll actually do the entire thing. So we have our data set. If we go all the way up to the right, we have two new variables, which are the movements. That's just the distance to the next frame. It exists for all of the observations except the last one, because the last one doesn't have a lead anymore, right? So we have one score less, which makes sense. Okay. So as always, how much does the left wrist and the right wrist travel until the next frame? We can visualize this for both speeches, and this is what it looks like. So we have two plots here. The movement of the left wrist for first speech in purple and the second speech in green. For reference, you see the speeches here again, so that we can check whether it all makes sense. And then we have the right wrist movement, second speech in green again, first speech in purple. So this is the first speech. Woman plus answers the second speech. What do we observe? For both wrists, we observe that there's higher values for the second speech, right? Second speech is this one where we have more movement, so this makes sense. Second thing that we observe is that only looking at speech 2, there's higher values for the right wrist compared to the left wrist. And if we look at this, so at some points, the speaker moves like both wrists, but then we have like those gestures only with the right wrist. When we look at it, it's the left wrist, but it's from the perspective of the speaker. So here, like this movement, that's reflected in those, this behavior of the curve here, those high values of the curve. Yeah.
Not by chance, or maybe you have investigated that, but is it like somewhat related to the strong hand, like that people normally use the right hand if they're right-handed? It's like in general, like right.
I remember that at some point in like the development, I saw that one hand was more predictive for like the human perception, and it was a little bit puzzling. I don't remember whether it was the left hand or the right hand. I can imagine that it's more common to gesture with the right, like with your strong hand, but I don't know. Yeah.
Just a clarification, we would need like a somehow normalized or standardized settings, for example, as in the videos,
so
to interpret the amount of movement.
Yes. So one precondition is that the camera perspective is stable. And it should also depict the speaker in the same size. Something that I didn't talk about is that this is actually not always true in the Bundestag, because the camera zoom changes a little bit. Another concern could be that a speaker who's taller does the same gesture, like the hand travels more just because like the arm is longer, which shouldn't make a huge difference, but it could introduce bias. What I do is I have a scaling step that scales those figures, those key point representations, to roughly the same size, no matter how strong the zoom is and so forth, so that the sizes of those speakers are always comparable. In this case, the camera is relatively stable, so it doesn't make a huge difference, but it's something to consider. Okay. But I think so. In general, I think it's quite nice, like what we see in the image and how we would want to quantify this. It's represented in those curves. We wouldn't work with data in such a granular fashion, but we would want to have some summary measure, which is why I average across those curves, so the left wrist and the right wrist, which is the remaining step. So for the measure of gesticulation of the first speech, I take the mean of left wrist, right wrist together, and this will give us those indicators. We were told that the first speech receives a lower value than the second speech, even though the values themselves are not very informative, but this is what we get. First speech 0.004, second speech 0.015. We can also visualize this. The speech by Klaus Ernst receives a higher value than the speech by Gabriele Heinrich, which is a minimum. Like, if this wouldn't be the case, then it wouldn't work, right? So those speeches are so different, they need to end up with different values. All right. This is the first indicator. Second indicator that we're looking at is the measure or indicator of posture, where we're interested in how high do those speakers raise their hands. Looking at this, Klaus Ernst does raise his arm. Gabriele Heinrich, she has like this short movement to the nose, but nothing else. So there should be some movement. What we're doing is we're calculating the height of the wrist relative to the shoulder. The shoulder is key point 6 and 7, left shoulder and right shoulder, and wrists are 10 and 11. We are only interested in the height, so we only need the y values. I'm not interested in whether it's here, like only like up or down. So the height of the left height is key point 6 minus key point 10. So left shoulder minus left wrist. Thinking about this is a little bit difficult because like the scale of the y scale is reversed, but calculating it this way will lead to higher values for lifting the hand, lifting the arm. And do the same thing for the right wrist, and then put those, or there's a third variable, whichever hand is higher, whichever wrist is higher, will be in max wrist height, so the height of the higher wrist, left or high. It's again a function that just adds those three variables to our data frame. So if you look at this, first speech again, all the way to the last variable. We now have the height of the left wrist, the height of the right wrist, and this is whichever value of the previous two was higher. Okay. I'm again going to plot this, and this is what the data now looks like. If we look at the y-axis, most of the time we have negative values, and this is because most of the time the hands are below the shoulders. For our first speech, Gabriele Heinrich, the left wrist is never above the shoulder, and the right wrist is also never above the shoulder. Looking at this here, this is what happens. She is like, the right hand goes close to the shoulder with this movement to the nose, but never above the shoulder. Makes sense. Klaus Ernst, he's having much more variation. He's also crossing the 0 line with both hands, which makes sense, right? He's lifting his arm. At the beginning of the video, he's moving with both hands, like both hands go up and down with this. And then at the end of the video, we only have with the right hand this gesture here, but nothing with the left hand. So again, looking at the data and looking at the videos, they are kind of synchronized. This makes sense. Also, if we think about averaging those numbers, Klaus Ernst should receive a higher score than Eva Heinrich. So we're doing this. We could, in principle, average across all or average across only whichever hand is higher. I'm using whichever hand is higher because it's correlated more strongly with human annotations, but this is kind of the only thing that was informed by like human coding and not really theoretically driven. Okay. So this is the average of max wrist height, so whichever wrist is higher. Again, first speech receives or ends or results in a lower score than the second speech, even though they are both negative. It's still higher scores are more or stronger postures. Also, looking at this graphically, you see the same picture as before. And I perceive this kind of as a proof of concept. It's not a validation, but it kind of shows you we can use this post-estimation data, calculate variables based on theoretical reasoning from it, and that capture what's going on in those videos. All right, this is the script I prepared. Any questions? Do you feel like you could implement this or like have any use for it?
That was my main question, like what research question could you answer with this data, or like what did you maybe, I assume you already applied this somewhere. What could you do with this?
So what I did is, I developed this in the first place as a methodological exercise in this context, so the context of the Bundestag. And then once it was developed, I applied it to the corpus of videos that were available 2 years ago. So until 2020, I think, 30,000 speeches in total in the German Bundestag. I mentioned it in the presentation shortly. So what I look at is this non-verbal effort variable. So those two indicators, and I also have one vocal indicator, but they are combined. And the results kind of draw one picture. And this is like the first application that I've been doing, nothing else so far. So I have the speeches where I calculate those indicators, and I have the text where I'm interested in how complex is the language in the speech, to get an idea whether complex arguments are put forward or whether there's simple arguments, simple language, maybe no arguments, with arguably or fairly rough measures, so like textual complexity. The main idea or the main motivation for this is that from a normative perspective in political deliberation and parliaments, we would like speakers, we would like politicians to present informed arguments that often require complex language, to weight different arguments against one another, like to have substantively good deliberation. This is one goal. On the other side, we would like speakers to deliver their speeches in a way that attracts the attention of the audience, because if you deliver a speech like this, then you will have a harder time capturing audience attention than if you deliver a speech like this. However, you could argue doing both things at the same time is difficult because gesturing requires cognitive resources and putting forward complex arguments. So the question was, is there a trade-off between the two, in the sense that I can either present complex arguments or I do a non-verbally appealing speech, but with simpler content. And I find this in the analysis, and I also find like this difference between government speakers and opposition speakers, where opposition speakers put more emphasis on the non-verbal delivery, but they use simpler language. Government speakers don't care so much about the non-verbal appeal or the non-verbal effort they put into their speeches, but they present more complex, or they use more complex language. I also connected this to data in the Landtag Baden-Württemberg, where I test the argument. So there I observe audience attention and can test the argument whether like those speeches that are non-verbally appealing will only do this with emotionality in the voice, not what I showed you here. But also like a non-verbal cue, emotion, like is your voice, vocal style emotional, or is it rather monotone? And does this also lead to more audience attention? And this is also the case. So we have this triangular relationship where to maximize audience attention, we need to put effort into our nonverbal delivery, but this will give us a harder time in putting forward complex arguments, which is the reason why we wanted the audience attention in the first place. So politicians they need to navigate this trade-off somehow. And this is the application that I followed in my research. I think there are more questions that can be answered. Yeah.
Another question that you can answer. So how much computational power does it take? You said you had 30,000 speeches. They're probably not this short.
So I didn't do it on this laptop. I also didn't do it on my machine, but it's a computer at Professor Kren's chair, which is reasonable. It's not like a high performance cluster or anything. It's reasonable, but it also wasn't super quick. It took me like 1.5 months or so, 2 months maybe.
Having it constantly running?
Yeah, more or less constantly running. It was 50,000 speeches actually, because it also contains speeches of like president, speeches that were filtered out, but it takes a while. It's also it certainly wasn't the most effective pipeline, because I never really tried to optimize it. For example, I had the videos stored on a external hard drive. So each video needed to make its way from the hard drive to the server, then being analyzed on the server. So this was probably a bottleneck that I never really tried to solve, because I was not in a hurry when I did this. I had many other things to do. So I can't give you an answer on what's like the minimum time you need. I also think that 2 months, like it's very different from what you would do in other research areas. But 2 months are not too long if you think about it as data collection, for example. It takes a while, certainly, but
How much space did all the videos take?
Oh, lots of space. 5 terabytes, 6 terabytes. Like even the output is pretty big. Like only the key points data is pretty big. Yeah.
Yeah, you have an estimation of how long this would take before starting it, and you probably like split it up, right? You didn't like that one piece of code start running over 2 months, so you probably like split up on different like subgroups, or like don't do like or what you do.
No, it's basically, so it's more or less the loop that I presented you.
For real, and then you just
So
what would happen if there like after 1 month there would be like an error in the loop and the whole code would break?
you can easily like
Okay,
it's a loop.
yeah,
Just
but did something
you
that
just
happened?
adjust the starting point.
Something that happened, or
So I had one problem that I also wasn't able to solve, where I don't know what, but something was loaded into the memory that I couldn't get rid of, and it would accumulate. So I would have to restart it every week or so, because it would break at some point. Now that I think about it, I'm not sure whether it was this loop or another loop. Like, I think this was actually fine. Maybe it was another thing. I can't exactly remember. It happens. That's for sure. Yeah.
do you have like a brief estimation how long 1 minute of speech video takes, or is like it's like every speech minute Like, does it take the same?
Yeah, so 1 minute of recording. In my pipeline with the GPU was like half a minute
Okay,
processing.
that's like the same mostly for every.
And
There could be also like speeches with like less.
no, it's no, that doesn't play a role. Yeah. Yeah.
I have one question. First of all, thank you. I think that's quite an excellent workshop to follow, and I think for my part I would feel comfortable analyzing something like the data set you presented. I wondered you previously also talked about the prerequisites of how a video would have to look like. You said like it should have one speaker and one camera angle. But apart from that, even if the speaker were to move around, for example, with a measurement of wrist against shoulder, you can
That should
still
work, yeah.
still work with that.
The angle, like the fixed camera angle, helps to have like so that different videos are comparable with one another. And that's why it's important. Like if you would change the camera angle, then you could try to scale the body sizes, but it would make things more complicated. And having only one speaker helps because you don't need to figure out which speaker to analyze. In the next step, I want to apply this to speeches in the US House of Representatives, where many speeches are delivered from within Parliament, so not from the speaker's desk. And so this requires some extra pre-processing. There are also multi-course models where, like, if there are two human detected, it would just do it for both, but then you have to figure out who's the speaker. This is all possible, but it's like it requires more work.
Maybe one follow-up question, if I were to, I'm coming more from like analyzing social media data and things like that. If I were to want to analyze a similar movement, but in a person who's doing a TikTok video, with probably some cuts in it, would it like, do you see an option there that it would work as well, the cut, even if you have like?
I saw, so last week I saw a study using post estimation for TikTok videos. There's also a study that uses it for campaign videos in the US. I have it on my computer. I can send that to you. I hadn't had the chance to read it in detail, but
okay, so there are approaches.
Yeah, there are approaches. Yeah.
Thank you.
For your presentation. I'm referring to audience attention and cognitive effort. Have you also looked at the complexity of movements? For example, the male speech on the right side here, we have different movements. He goes like left, right, up, down, like crazy diagonal. But there might also be a person who does really big gestures, but always the same gestures. So I mean, this could be less cognitive effort in a way. Did you look at that as well?
No, I'm interested in it, but I didn't. So what I presented, like those measures, more or less, this is where I am in my research with this sort of data. But yeah, I think because like it forces you to think about the form of movement, and this kind of leads to those thoughts like, what do they look like? How do speakers differ? So I think there are possibilities to work with this into that direction. I think in the TikTok study, they kind of classify different gestures based on this data. Not sure how. I think I only read like the abstract and skimmed through it, but it seemed interesting.
And since you've done all this crazy computations, is there any midterm plan to release this JSON data basically? Because as I understand, at the end you don't need like the video data in itself.
Yes,
basically, it's just enough to release the postures.
yeah. So for the paper that's a working paper, my goal is to add the US case to that and try to publish it. And that would be the latest point where I would be very happy to share the data. I would also be happy to share the data beforehand if anyone's interested. It's quite big again, but.
So there are still like a couple of minutes left if there is another question. Online, all right. So in terms of the existing literature, is there something like an existing list or common movements and their significance developed by anthropologists or even kinesiologists who could help generate common movements? A better meaning.
I tried to find something, but I couldn't yet. I'm not aware of anything. I can't guarantee that it's perfectly possible that I just wasn't able to find it, but I didn't. So I don't know.
All right. So thank you, Ollie. Maybe. Insightful talk and workshop. I think it's really helpful for a lot of us. So the next event in SSDL will take place on October 30. Jessica Dykala from GESIS will give an input talk entitled From Evidence Gap Maps to Systematic Reviews and Meta-Analysis, Approaches, Techniques and Tools. With that, thank you for joining us today and see you soon.